begin, let's consider the following table. We'll have x be our independent variable and f of x be our dependent variable. We'll be looking at the function f. F of 0 is negative 17, f of 1 equals negative 14, f of 2 equals negative 11, f of 3 equals negative 8, f of 4 equals negative 5, and f of 5 is left as our question. If we had to make a guess or conjecture as to what f of 5 is, we might naturally try to find some pattern. Here, one pattern that might arise is looking at how f of x changes. We go from negative 17 to negative 14. That's a difference of 3. Negative 14 to negative 11. Again, a difference of 3. Negative 11 to negative 8, a difference of 3. Negative 8 to negative 5, a difference of 3. It might seem pretty reasonable that we would see again that difference of 3, giving us our conjecture that f of 5 equals negative 2. And that would be a very reasonable conjecture. Let's look at another function. Let's use g of x. Let's consider g of negative 2 to be 9, g of 0 to be 7, g of 1 to be 6, g of 2 to be 5, and g of 5 to be 2. Our question will be then, what is g of 6? We could try to look again for that pattern, and we'd see that from 9 to 7, it's a difference of 2, a decrease of 2. From 7 to 6, a decrease of 1. 6 to 5, a decrease of 1. 5 to 2, a decrease of 3. Because just looking at the change in g of x being not consistent across this table, we might not be able to use the same reasoning directly that we did before to answer what g of 6 was. In fact, this change seems maybe less consistent. However, there is a difference between these two tables. In the second table, the x values don't change at the same rate. So in the first table, it goes, x starts at 0 and goes up by 1 in each column of our table. In our second table, it does not always just go up by 1, which means our first method of just checking how much the f changed might have been oversimplistic, and we may have just been able to have been satisfied because of that change. So let's think of how we can keep track of that change in g. Well, we can do that by keeping track of the change in g with respect to the change in x. So again, we're going to look at how g of x changes as the x value changes. We're going to look at this as a ratio, and we're going to have the change in g over the change in x. So let's look at our first two pairs in our first two columns, rather. We have negative 2, 9, and 0, 7. The change in g for those first two pairs can be seen as 7 minus 9. And as our denominator, it would be 0 minus negative 2. Ultimately giving us negative 2 over 2, which reduces to negative 1. Let's try the same procedure for the third and second columns. We'd have 6 minus 7 over, change in x being 1 minus 0, and we'd get negative 1 over 1, which would be negative 1. We can try this for one more, because if this is consistent, it should be true for all of them. So let's try another to see if it's still as consistent. Let's try it between our fifth and fourth entries. So 2 minus 5 over 5 minus 2, giving us negative 3 over 3, which is again negative 1. I just wrote something wrong, but I'll correct. This tells us that for every change, positive change of x, we'll see a change in g by negative 1. So for every increase in 1 of x, we'll see a decrease in g of x by 1. And sure enough, negative 2 to 0 is an increase in x by 2, and the decrease, g, decreases by 2 to 7. So if we follow that logic, 5 to 6 would be 2 to 1. Whenever a function has this constant rate of change, and we'll use the word slope to talk about this rate of change, then we say that the function is linear, and we can call it a linear function. Linear function has the nice property that it can be expressed in the form y equals mx plus b for some unknowns m and b. Here, if we know what the slope is, then we'll know what m is. We'll say that m is that rate of change. M is slope. Let's do an example of this. In fact, let's try to find m and b for the function g that was introduced in that second table. If we think that g of x is linear, which our few examples or our few checks seemed to show, then that means we should be able to find an m and a b that satisfies every entry in this table. According to our table, we know that g of 0 equals 7, so we can write that down. According to the formula that we want to use, we would get that m times 0 plus b is g of 0. So we know that g of 0 is just b. So we can find that b is going to equal 7. Now again, we've said that m is slope, and before we found what we believed to be slope of negative 1, we could just use that. But let's look at a different method. We know that g of 1 equals 6 from the table, and from our formula we can get that m times 1 plus b would also equal g of 1. If we plug in our value of b, which we found to be 7, then we would get that 6 equals m plus 7. that consequently m equals -1, which is exactly what we thought it was. Altogether, we can express g of x as a function -1 times x plus 7. And we can graph this. We can label our axes x and y. I might call it g of x. I'm going to rechange that later just because I want to label the graph itself. We can graph some points. We have the point 0, 7. We have the point 1, 6. We have the point 2, 5. We have the point 5, 2. Hopefully. Perfect. 5, 2. And sure enough, we can connect those points with a single line. That line we'll label G. I think it's at this point that I recognize that I gave maybe a poor name for that other axis. Notice that g of x is straight. Well, that plays into its name of being a linear function. If a graph of an equation is straight, then that means it has a constant slope. That's another way to identify that it's a linear function. Here, when we introduced slope as rate of change, we can see that again, of the x value increased by 1, meaning the y value decreased by 1. And here, there is an increase of x by 3, and so there is a decrease in y by 3. And an increase by 1, decrease by 1. All of that points to the slope being -1, which is again what we found at this point using two different methods. At this point, also note that in this line, in this graph, we see that our function g of x crosses that y-axis at the point y equals 7. Because it crosses at that point, we're going to give that a special name, call it the y-intercept. And you might recall when we solved for g of x, we found that b was 7. And sure enough, b will always be the function's y-intercept, the point at which it crosses the y-axis. It can also always be found by plugging in for x equals 0. That's by definition what the y-intercept is. Let's look at some more examples. We'll graph 3 lines. I think red and purple might not be the best colors. They seem a little hard to distinguish. I'll be more mindful of that in the future. So we have 3 lines F, G, and H. We have a few points of those lines labeled as well. Let's calculate the slope of f. The change in the y value is 5 minus 3 is 2 over the change in the x values, 4 minus 0 is 4. So we'd end up with a slope of 2 over 4, which is slope being 1/2. Let's look at the slope of the function g. We have the point 1, 1 and the point 2, 2. The change in y, 2 minus 1 is 1. The change in x, again 2 minus 1 is 1. So we'd have 1 over 1, which is just 1. And finally, we have the slope of h. We have the points 0, 5 and the point 1, 1. 1 minus 5 is -6. And 1 minus 0 is 1. Sorry, 1 minus 5 is -4. So we have -4 over 1. We have a slope of -4. Now I'll also note we can see the y-intercepts of each of these lines by looking at when it crosses the y-intercept. Because that's the b value, we have enough information to give the formula for f, g, and h. But let's look at what some of these concepts of slopes looks like. A bigger slope corresponds to a steeper line. Note how g is steeper than f. And a negative slope is a line that kind of goes down when reading from left to right. Now f and g are kind of going up, and sure enough they have a positive slope, whereas h goes down and has the negative slope. You might know from geometry that 2 points is enough to define a line under most geometries. And similarly, because our linear functions can be thought of as lines, 2 points is enough information to define a linear function. Let's do an example of this. And let's find the function. I guess I start with just the slope of the line that goes through the following 2 points. 1, 2, and 6, 7. We could extend this question if we want to find the entire equation. Remember, slope we're going to think of as the change in g, or change in y over change in x. We might use the words rise over run, or this triangle y over triangle x. It's the Greek letter delta referring to change in. We'd be given 7 minus 2 over 6 minus 1, which is 5 over 5, so it has slope equal to 1. Let's find what the y-intercept is. Again, to do this, we might want to remember that the formula for a linear equation being y equals mx plus b, we know that m equals 1, and let's just use one of the points that we know our line goes through. Let's use the point 1, 2. So we can make the substitutions for y, m, and x to get that 2 equals 1 times 1 plus b, which will give us that b equals 2 minus 1, which is 1. Altogether, the line through 1, 2, and 6, 7 has the form, or can be expressed as y equals x plus 1. Let's quickly look at an example of some function that is not linear, just to see something else. We have the familiar table setup, the point 0, 0, 2, 0 0.5, 4, 1.5, and 6, 4.5. We might be asked, is this a linear function? To show that's a linear function, we might be trying to find m and b such that we can express this function as y equals mx plus b, or we can show that no such m exists by showing that it does not have a constant rate of change. So let's find its rate of change for two of the points we know. Let's use the first two. 0.5 minus 0 over 2 minus 0 gives us 0.5 over 2, which reduces to 4. Let's use another 2 points to calculate the rate of change between those 2 points. 1.5 minus 0.5 over 4 minus 2 gives us 1/2. Sure enough, 1/2 does not equal 4, meaning we do not have a constant rate of change. Because it does not have that constant rate of change, it's not a linear function. Because of that, we can conclude that there does not exist any m and b such that y equals mx plus b. Can't be found. Let's do another example. We're given an imaginary print shop, and we make the assumption that the costs at that print shop follow a linear model or a linear function. And suppose it costs $1.30 to make 10 prints. And suppose they also tell you that it costs $1.72 to make 16 prints. And the question might be, How much would it cost for 25 prints? To break this down, we want to use the information that we know that it's a linear cost function. This immediately tells us that any expression to model the costs can be expressed in the form y equals mx plus b. We can also identify some of the information, namely that 10 prints costs $1.30, to mean that our function would go through the point 10, comma 1.3, and we could similarly get the point 16, comma 1.72 by using that other piece of information. To find m, we might recall that m is slope, so we can calculate the change in the cost divided by the change in the number of prints. Altogether, we'd get 0.42 over 6, which will result in 0.07 as our slope. We'd also want to find what our b is, or what our y-intercept is. Here we can do that by using our form, our general form of y equals mx plus b, and use either of the points we know of to get that 1.3 should equal m, which is 0.07, times x, which in this case is 10, plus b. Then we can work to rearrange and solve to get that b is going to equal 1.3 minus 0.7. And that b equals 0.6. Altogether, now we can express our function as y equals 0.07x plus 0.6. To answer the question, which was asking about the cost of 25 prints, we'd want to use 25 as our x and plug it into the function that we just constructed. To get that y will equal 0.07 times 25 plus 0.6. Which equals 1.75 plus 0.6, or 2.35. In the context of our question, 25 prints will cost $2.35. And although unasked, we can interpret some of the other things we found along the way, that every additional print costs 7 cents. And that in one way, 0 prints still has a cost of 60 cents, so maybe we could think of it as the cost to access the printer at all costs 60 cents. We'll have one more section of new material, being interpreting parallel and perpendicular lines. And again, I'm apologizing for that red-purple colors. I'll use some different things next. So let's say we have two lines that are parallel. Well, we say that two lines are parallel if we kind of think of their infinite extensions never intersecting. And in a similar geometric sense, we can define perpendicular to mean that the two lines intersect at a 90-degree angle. However, both of these are geometric statements about being parallel or being perpendicular. They're based off how the function, in these cases, look. Let's phrase both of these properties in terms of the functions themselves. Being parallel can be similarly stated to mean that the functions or the lines have the same slope or equal slope. In this case, it looks like our lines f and g both have a slope that's about 1. To be perpendicular is to mean that the slopes of the two functions are negative reciprocals of each other. I'll write down what that means later, but I can say it now. The negative reciprocal of some number n is negative 1 over n. So negative means you negate it or put a negative sign in front of it. Reciprocal means put a 1 over that number. Or if it's a fraction, you can think of as swap the numerator for the denominator and vice versa. So, as an example, you might be asked to find the equation of a line that is parallel to a given line. In this case, we'll use the line y equals 10x plus 2, and that goes through another point. In this case, that goes through the point 3, 7. So what's the information that we know? We can recall that parallel lines have the same slope, and in this case the slope of the line y equals 10x plus 2 is 10. So we know that the slope of our function we're trying to construct will be 10. Again, in our general expression, if we use y equals mx plus b, we know m. To find b, we can use any point we know that the function goes through. We can use 3, 7 to get y, which is 7, equals m, which is 10, times x, which is 3, plus b. To be 7 equals 10 times 3 plus b. Or that's 7 equals 30 plus b, meaning that b equals 7 minus 30, which means that b equals negative 23. Putting it all together, we get that the line parallel to y equals 10x plus 2, and that goes to the point 3, 7, is, or can be expressed by y equals 10x minus 23. And I made some errors writing around, so I'm rearranging. Let's find the line perpendicular to y equals 2x minus 4. That also passes through a given point. In this case, it's a line that passes through three, 6. So what do we know? We know that perpendicular means that the slopes are negative reciprocals of each other. And here we have the line y equals 2x minus 4. So its slope is 2. And the negative reciprocal of 2 is negative 1/2. So negative and then 1 over 2. And again, before, to find the other part of the equation, let's use a point that it goes through. We know that it goes through 3, 6. So then we can get that 6 equals negative 1/2 times 3 plus b, to find that b equals 6 plus 3/2, which should hopefully equal 15/2. Altogether, that gives us y equals negative 1/2 x plus 15/2. That'll be it for 1.3.